All right, so I didn't see. Any questions from last time? All right, so we're going to go over the problem that I gave you, the homework. If somebody could douse the lights a little bit, I'd appreciate it, please. Thank you very much. Okay. All right, so this is now online. I was online yesterday too, and the day before. All right, this is the handout. It's part handout, part homework. If you did it, it's fine. If you didn't do it, the answers are now online. This is what the answer is. We talked about tonicity, right? Tonicity really is a determinant of what happens to a cell. It's closely associated with osmolarity, but it's not the same thing. One is technically measuring what happens to a cell, right? So bigger, smaller, no change, right? Not very quantitative, more qualitative. And then osmolarity is something you can measure. It has units. Okay. So the example question, what will happen to cells if you add an isotonic solution to the human body? This is the very easiest possible question you could have. Okay? Can't get any easier than this because we've sort of eliminated a lot of things. So what I'm going to do is I'm going to take you through how I would work a problem like this. You're going to see something much more challenging than any of these on your exam. But again, we're going to crawl, and we're going to walk, and we're going to run. So I like to start my students off, and this is we're going to think like this throughout the semester. So what do we know? Right? That's the first thing you have to do. What do we know? And the nice thing about this type of question is there isn't a lot that you could possibly know, but there is some things you can know. So just because I have an answer that's good doesn't mean that I wrote down every possibility, right? Just after a while, I'm like, yeah, this is good enough. We can go through it, right? So what do we know? We know an isotonic solution is a solution that does not cause a change in cell volume. So you already sort of know the answer. When you put a cell in an isotonic solution, nothing's going to happen on a net scale, right? The cell won't shrink or get bigger on a net scale. Might it change shape a little bit here or there, just randomly? Sure. Okay. So you know that. Isotonic completely ignores penetrating substances. Now, we haven't talked about that yet. Okay, so there is a handout that I gave you. Okay. And that handout looks like this. So it's a good time to actually talk about it. It's called the hierarchy of penetrating substances, entry into cells. Okay? And you can read the description. But I'm going to focus on this graph. Okay, so let's talk about this. So on the y-axis here, you have permeability. Now, we've already talked about permeability when we talked about flux. Remember the flux equation? We've sort of insinuated permeability. We're actually going to come back to permeability when we talk about golden Hodgkin cats in the nervous system. So, again, these are concepts you can't just learn them and forget them. It doesn't work like that in this class. That's the kiss of death. Right? So on the y-axis, permeability, which means how easily a substance moves through a membrane. The more permeable the membrane, the easier the substance moves in the membrane. Excuse me. Okay. And then there's what's called a partitioning coefficient. The bottom line is, I don't really want you to focus on the partitioning coefficient, but the partitioning coefficient is where the subject, the molecule, the ion ends up staying. Where does it partition to? The extracellular fluid, inside the membrane, intracellular fluid. We're not going to worry about that much. On here you have a list of penetrating substances. What does that mean? Okay. Methyl alcohol, ethyl alcohol, urethane, and you've probably heard of some of these substances. Propylene glycol, monocetin, urea, and glycerol. These are all substances that on their own are able to penetrate the cell membrane. So even if they're not hydrophobic, they actually work like a hydrophobic compound. Okay? The substances that are in these easy problems here are all what are called non-penetrating substances. Ions, glucose, right? They cannot go from the outside of the cell to the inside of the cell without help. They need some kind of help, a channel, a transporter, endocytosis. But these substances, they get in. So let's take ethyl alcohol, one of your favorite compounds, right? Ethyl alcohol is able to penetrate your stomach. You can actually start absorbing alcohol before it gets into the duodenum, right? Because it's a penetrating substance. So there is some truth to the fact of the matter that if you go and you eat a big, fatty, heavy meal before you go drinking, it will slow down the absorption of alcohol. First of all, fat slows down digestion. But the more of it you put in your stomach, the more difficult it is for the substance then to get into the blood. It's a penetrating substance. It works really well, in case you didn't know. Okay, so you have to memorize this list. You not only need to know the substances, but the level of penetration. So methyl alcohol, which will pickle you, by the way, methyl alcohol is dangerous. It will kill you. How does it kill you? It kills you by being converted to paraformaldehyde. Paraformaldehyde is what we embalm the dead with. It basically glues your cells together. Really, really, really nasty, nasty, nasty stuff. So methyl alcohol is the greatest penetrant. So it's the easiest thing. So it makes it even worse, right? So drinking ethyl alcohol is one thing, but drinking methyl alcohol happens even faster. And then glycerol, which is the backbone of the phospholipid bilayer, right, is the least penetrating. So the more penetrating something is, the more quickly it moves from one side of the membrane to the other. So you need to know that. So you need to know the difference. You can read through this little explanation here, and so it's kind of like a cheat sheet for you. All right? So we haven't talked about it yet, but penetrating substances, this is a list of the ones I want you to know. Don't worry about partitioning coefficient. I'm going to ask you anything about partitioning coefficient. A little bit too advanced of a topic for this class. Okay. So isotonic completely ignores penetrating substances. We don't care if there's a penetrating substance in there. Now, do we know if there's a penetrating substance in there? We don't. Okay? We don't. And I'm not going to talk more about penetrating substances right now because I think if I do, I'm going to confuse the heck out of you, and I don't want to do that. This isn't Word, so... All right. And there's more stuff we probably don't know. So I want you to try to list. I want you to be very methodical with this, because the more methodical, this is like doing a math problem, right? The key to doing math, well, for most people, they don't realize this is just being organized and methodical. Math isn't that hard, you just got to know the rules. So you start with what you don't know and say, okay, well, I don't know this stuff. Now what do I do know? Or what can we safely assume? We do not know the osmolarity of the solution. You don't. I never told it to you. I didn't even tell you what the solution is. If I said that we placed a cell in extracellular fluid that came from a human being, could you make an assumption about the osmolarity of the substance? Yes, because I asked you to memorize it. So then you could say, well, I don't know for sure because there are differences amongst people, but it's probably about 300 milliosmolar, 295 milliosmolar. But it's still an assumption. I don't know that for sure. But it's a good assumption. Okay? We do not know if there are any penetrating substances. It doesn't tell us. We just don't know. Right? We do not know what the ionic makeup of the solution is. We have no idea what the hell's in here. We just said it's an isotonic substance. No idea what it is. We can assume that because there's no specific mention of what the person's osmolarity is, to whom we are adding the isotonic solution, that the osmolarity is 300. So you can make this assumption anyway, even if you don't know it came from a person. Doesn't mean it's right, they're assumptions. But you have to let me know that you know it's an assumption, right? That you could be wrong. Versus we know this for sure. We assume that the person is otherwise healthy, meaning the cells. right? And we'll get to this why in a second. We also assume that the isotonic solution is being added via an intravenous infusion. So this is a human physiology course, so I'm going to try to keep things as clinical as we can. It makes it more interesting, right? So there's two ways to get these solutions into your body. One is you can eat it, drink it. The other one is to do what you would do as a clinician, right? You put it in via IV catheter. That's how they do it in the hospital, so that's how you're going to do it in this class. It doesn't magically just get in there. Okay? You may think. Not that I'm against magic. Big fan, right? But not in this class. Unless I ask the question, and I change the rules, because I'm allowed to. Because I'm a wizard, right? Okay. You can't, but I can. Sorry. All right. So, IV infusion. We do not know the volume of the ice. We didn't say anything about the volume either. I have no idea how much we injected, right? This is easy, right? Because there's a lot of stuff that you just don't know. But it makes you think. And so you have to start there. Then you have an explanation of the process in red. I do the same thing for the second problem, and then the third problem, you're on your own, because I want you to struggle with it. All right. Explanation of the process. So I like to think very methodically. So if I'm doing this experiment, how would I do it? Well, it's in a human, so you could say they drink it, which is fine. It's a little bit more complicated. If they drink it, then it's got to go through a slightly different process, but you got to explain it. If it goes into the blood, it's a little easier to understand. So the isotonic solution is infused into the medial cubital vein. The medial cubital vein is right over here. It's one of the ones that they use to draw blood, because it's, at least in men, it's huge. And depending on women, how lean that woman is, it's pretty easy to hit. It's like a canal, right? And so that's why they go after it. Is it the only one? No. I don't care. You could just say a vein in the arm. That's fine. I'm not going to hold it against you. But it's a vein, not an artery. Not a good idea. Unless you're an anesthesiologist, you don't want to hit an artery. Bad. Okay. All right, and 23 gauge needle, and you don't have to put that down. I just put it in here to make it sound better, right? All right, the volume of blood vessels increases by an unknown amount. So it's going into the blood, right? So you have to tell me what happens to the blood. Now, if we knew osmolarity, we could then make a statement about what would happen. So if I infuse something into the blood, right, if I'm adding water to the blood, isn't the amount of fluid in the blood going to increase? Yeah, of course it is. You're adding something, right? So, into an unknown amount. The osmolarity of the blood vessels may have changed, but we cannot be certain, because you don't know what the osmolarity is. Okay, so notice that this is a step-by-step process. Don't skip steps, because that's going to lose your points on my exam. Right? You've got to be methodical. I'm teaching you how to think. It's very painful to do it this way, but by the end of the semester, you'll get it, and you won't make foolish mistakes. And that's what I'm trying to prevent here. So I'm teaching you how to think with this as the prime example, and then the entire semester you'll do the same thing. You'll get, oh, well, this is the way we do it, right? Okay. The isotonic solution is circulated throughout the circulatory system. You inject it into a vein, it's going to go everywhere. You've got to tell me that. I don't know what you know. I cannot make any assumptions. If you don't write it down, I'm going to assume you don't know. And I'm going to mark it wrong. Right? I can't just assume because I know that you know. The isotonic solution diffuses out of the capillaries. Now, we haven't gotten to this yet, but capillaries are the smallest blood vessels. That's where the majority of diffusion occurs in your body. Okay, it's not going to diffuse out of your aorta. That doesn't happen. The superior vena cava. Right? It's capillaries. So you have to know a little bit of anatomy here, but it's functional anatomy. The volume of the interstitial fluid then increases. So the substance moves from the blood, diffuses out of the capillaries. You know what diffusion is now, and now it's in the interstitial fluid. Okay? What can you say? We cannot be certain as if there's any change in the osmolarity. Why? Because I didn't tell you what the osmolarity is. If I didn't tell you what it is, unless you have magical powers and you can see, you can't tell me. You don't know, right? because the solution is isotonic, we know ultimately that the cell will not swell or shrink, but through random diffusion, fluid exchange may occur between the interstitial fluid. You could add another step in here, which I skipped, is that there's a change, that the volume of the interstitial fluid increases. Then you can say that this statement here is if it's going to move in or out of the cell. And that's what this is. So is it going to move in and out of the cell? On a net basis, no. But it will move in randomly. Okay? If we were hypertonic or hypertonic, it changes the story. So the cell may have temporarily changed its shape. For instance, if that was a typo. There are unaccounted for penetrating substances that are part of the isotonic solution. When the penetrating I'll have to fix all these typos. All right. When penetrating substances move quickly down their concentration gradient, they temporarily hold extra fluid with it. Okay. Penetrating substances don't have a net effect on the cell, but they can temporarily, if there's a high enough concentration, pull water. Because these penetrating substances have a mass. And because they have a mass, anything that has a mass, if it moves fast enough and in a high enough quantity, will pull water with it. Glucose actually does this in your kidney tubules when you're diabetic. It has such a high mass that it actually pulls water from being reabsorbed and you make more urine. Okay, but this happens at a very fast rate. So does water movement go in and out of the cell? Yes. Does the volume change temporarily? Probably, but grossly, at net level, no. Okay. So in summary, so then you can summarize it. Okay. So this is a summary. Again, this is the easiest problem you can have. So the blood vessel volume increases compared to the beginning, right? The osmolarity doesn't have a change. No change. We don't know, really. So we're just going to say no change because we don't know. The interstitial fluid volume increases with simultaneous decrease in blood vessel volume, right? So it went up because you infused fluid into the bloodstream, and then as some of that fluid moved from the bloodstream into the interstitium, then the volume of the interstitium went up, but the volume in the blood vessel went down. Osmolarity, no change, because we just don't know. And then in the cell, there was no net change. That's it. Okay? That is, again, the simplest form that I can give you. Every one of them gets more challenging. The more information you have, the more difficult it becomes, to some degree, because you have more information. Okay. Questions on that? Did anybody actually try this and not get anything like this, Marissa? Yeah. How did you do compared to this, relatively speaking?
I mean, I didn't really include like the IV and
yeah. Okay, but that's an additional piece. But did you get the gist? So really, all I wanted you to do is see if you could get the gist on your own, and then we can fill in the details. So now Marissa can go back and say, okay, well, I'm going to be a little bit more methodical. I can add the IV portion because I didn't know that before. Does anybody not follow this logic? I mean, I can diagram this out too. It would take a long time, which I don't have time for. But you get the sequence of events. You see, I'm trying to be more methodical. And I actually could have, I'll get the typos fixed, but I could have added more steps in between too. But this is sort of the bare minimum you would have to do to get full credit on a question like this. Now you have an answer to a simple question. The next one is a little bit more difficult. All right, so we'll go through that one real quick. And then the third one, you're on your own. If you want me to check it, you look at it, you want to run it by me, it's totally up to you. But I want you to struggle with it, because if you understand the first two, in theory, you should be able to do the third one. Okay? And so there's a bunch of information here that you can read that's helpful to you. Question number one. What would happen if you added a hypertonic solution of sodium chloride? Now we have more information. It's a little bit more complicated now. To the extracellular compartment. Show the differences by changing the size and the volume of the ICF and ECF compartments. Give all your rationale. Again, there isn't enough answer. The correct answer only gets you a small amount of credit. So here, who can tell me what's going to happen to the cell? So you know the answer right away. A hypertonic solution is going to cause the cell to do what? Right. So that you know, but that's at the very end. But if that's all you write, you're going to get 2 points if it's a 20-point question, right? You don't want 2 points. So you're going to have to go through the steps. Again, we start the same way, right? What do we know? Hypertonic solution that makes the cell shrink. Hypertonic completely ignores penetrating substances. The other thing you know, and I didn't put this in here, and again, I was sort of in a rush when I did this, but you can add we can go through it. You know that it's sodium chloride. So it's essentially an IV bag that you'd be giving somebody in a hospital. Now, it's a hypertonic solution. In a hospital, it would be isotonic. Okay? So you can make some assumptions based on that. So you could write down, we know that it's sodium chloride. If you know it's sodium chloride, then you also know what? About at least one of the substances. Sodium chloride is what type of substance? Is it penetrating or non-penetrating? It's a non-penetrating. So you could write another one that says it's non-penetrating. Do you know if there's penetrating in there? According to what I give you, we don't. We can assume there isn't any because I told you there. I didn't say there was. So you can say, well, according to the information given, we can safely assume that there are no penetrating substances. If there are, we're not aware of them. Okay? What do we know? What can we safely assume? We do not know the osmolarity of the solution. We don't know if there's any penetrating substances. Again, a lot of this I just copied and pasted because a lot of it was very similar to the last one. We can assume that there's no specific mention of the person's osmolarity. So in this case, I told you it was a person, right? So we can assume we're going to have to go at 295 and 300 milliosmoles per liter because that's normal average for most people. It's a reasonable assumption given the information that you have. And that's really what I'm looking for. Can you see the big picture, take the knowledge that you know, and then apply it in a reasonable way? That's what you need to be able to do. We assume the person is otherwise healthy because if the person is not healthy, it may change this. But then I'd have to tell you something about it. It's too early to do a question like that. It could be on the final type of thing where you've learned all of the systems and you have enough information. Now, if they're unhealthy, you need to make some assumptions. But you're not ready for that. All right. Intravenous, we can do the whole intravenous. We do not know the volume of the hypertonic solution. So I didn't tell you we added 100 mils. We added a liter. I don't say anything about that. So you can't even make an assumption. It's an amount, an unknown quantity that can be measured. So we'll go through the explanation. And a lot of it's the same as in the other one. You'll notice the same thing. So we get to the capillaries, right? The volume, you inject it into the blood, the volume of the blood goes up. It doesn't matter what the solution is. If you add volume to something, the volume has to increase, unless there's a hole, right? So we're taking this step by step. So you add it to the capillaries, then it diffuses out. So what happened to the volume in the capillaries when some of it diffuses out? Did it go up or down? So if I added water, sodium chloride solution to your blood, let's say I added a liter, right? And then some of it diffuses out of the blood into the interstitium. What has now happened to the volume in the blood? Has it decreased or increased? It has decreased compared to the injection, but is it still higher than pre-injection? Yes. That's something you have to keep in mind. So when you're wording this, you have to be very careful with your wording. So you got to write well, right? You got to be clear. Is it compared to pre-injection that we're talking about, or is it compared to the injection? It makes a difference. It really does, right? Because the answer's a little different. One is decreasing, the other one is still up, but it's lower than one. Okay? So, interstitial fluid. You don't know about osmolarity changes here because I didn't tell you, right? So a lot of this is similar. We know the cell will shrink. Then what happens is the volume of the ISF, due to water leaving the cell, will move down its electrochemical gradient. So what will happen to the cell is shrinking, but what's now happening to the level of water, the volume in the interstitial fluid? You had the fluid move from the blood vessels to the interstitial fluid. Volume went up in the interstitial fluid. Now, additional water comes out of the cells into the interstitial fluid. So now what happens to the interstitial fluid? It goes up again. So it's a double whammy, right? It's getting water coming in from the capillaries, and then it's going to get water coming in from the cells. So the extracellular compartment is actually getting bigger. So you're getting swollen, is essentially what's happening, right? You're retaining water between your skin, right? Because that's where it is. If it's in the cells, you don't see it, but it's outside the cells. So then what happens to the volume inside the cell? Well, it decreases. So if the volume inside the cell decreased, the volume of water inside the cell decreased, what must have happened to its osmolarity, even if you don't know what the osmolarity is? What has to have happened? It has to go up, right? It has to, but you just don't know how much. But it has to go up. If you lose water from a solution, there is more solute. If the definition of osmolarity is the amount of solute per volume, then it has to have gone up. The osmolarity has to have increased. So if it was 300, it's above 300 now. It has to be. Right? So you can then summarize if you want. I suggest it. It's a good idea. So blood vessel. The volume increased. The osmolarity is unknown in this case because it didn't tell you. The interstitial fluid, it increased with a simultaneous decrease in blood vessel volume. Osmolarity is unknown. And then cell volume decreased. Here you do know what's happened to the osmolarity. I said unknown. There you actually have an increase. This is wrong. That's wrong. Fix that. Okay? It has to have happened, right? If you're losing only water and all of the particles stay, then if you understand what osmolarity is, then it has to have increased. If you gain water and the same particles stay, then what has to have happened to the osmolarity? It has to go down. So this one's a mistake. So this is the osmolarity will decrease. Okay, questions on this? So these are the types of things you're going to have to do. I actually have another problem that was done by a student last year. It's got Carrie's name on it. And that's another practice problem that you can do that's a little bit harder than these. So there's one more here that you can do for practice. It's a hypotonic solution. So again, just finish the trio, right? We did isotonic, we did hypertonic, now you do hypotonic. And then Carrie's is a little bit different. But what I'm going to do on the exam is I'm going to give you all kinds of information and then not give you other kinds of information. Right? I may tell you that there's penetrating substances, I may not. I may give you molarities of stuff, I may give you all kinds of stuff. So that leads me to the next handout. This one. This handout says from moles to milliequivalents. Okay. So, this is review of chemistry. I'm assuming you learned this at some point. I don't know for sure. I don't know. Again, another cheat sheet, right? Assuming nothing. Another cheat sheet with some definitions on it. And on the back, there are example problems with answers. So you go through the concept, you do the example problem, there, and then the answers in red. So you're going to need a calculator in this class, a scientific calculator. Okay? Because you're going to have to be able to do logs at some point and ln's to natural logs. basic. I just bought one. Mine broke. Where is it? Yeah, $10 at Target. So if you don't have one, $10 at Target. You don't need a $150 graphing calculator that you can do algebra with and calculus. All you need is a simple calculator right here. So if you don't have one, pick one up. Okay, so moles, right? Moles is a number, right, of the number of particles, right? So a mole of any substance is the same number of particles. This should be a review, I hope. Right? Mole of any substance is the same number of particles. Molarity means moles per unit volume. It's liters or mils. In the human body, we use millimoles and milliliters. Sometimes you go liters. So you've got to be able to do conversions from liters to milliliters and from osmoles to milliosmoles. So you have to be able to do what's called factor analysis, which is something you do in chemistry or did in chemistry, right? Math. And so we take you through here. So if you look at that chart of substances I gave you to memorize, intracellular and extracellular, it's both in millimoles and milliequivalents. In the case of what you're looking at, they're the same, but they're not always the same. Remember the difference, right? Remember the difference. Milliequivalence is essentially what it takes to combine of a substance with 1 mole of hydrogen ion. That's the technical definition. But I look at it more from the charges perspective. Okay? So again, if you're looking at two substances, glucose and sodium chloride, right? If they both have the same molarity, moles per liters, right? They're both 50 moles per liter. Right? If you put the glucose in water, it still ends up being 50 osmoles per liter, right? It doesn't change. So the unit changes, but the number is the same. If you put the sodium chloride in water, what happens to the sodium chloride? It dissociates. So now you actually have 100 milliosmoles per liter, or 100 osmoles per liter. Okay? The milliequivalents are like osmolarity, except you're really looking at charge. And so on the bottom here where it says remember, okay, right at the very bottom it says for monovalent ions, 1 milliequivalent equals 1 millimole. So sodium has a +1 charge. Chloride has a +1 charge. Potassium has a +1 charge. Those are monovalent, right? The outer shell, that's what we're talking about. Okay? So 1 milliequivalent equals 1 millimole. If you look on the back, on the top, for a divalent ion like calcium, magnesium, 1 milliequivalent equals half a mole. You could flip that around and say a half a milliequivalent equals a mole, millimole, right? So it's you could flip it around. Excuse me, it's the other way. It's 2, excuse me. So half a milliequivalent equals 2 millimole. You could flip it around. And then on the bottom of that, it says for a trivalent ion, right, something like phosphorus. It has a P-3 on it, right? Then 1 milliequivalent equals 0.33. You need to memorize these conversions. You have to. If you don't memorize the conversions, if I give it to you, you're not going to know what to do with it. Right? So just straight out memorize the conversion factors, however you want to memorize it. So in here, then, and I'm not going to go through this because I've got this, I'll certainly answer questions once people have tried it, but I've got sample problems here, and then I've got the solution and the answer. So if you have a problem, let me know. And you got to know how to do factor analysis, so you got to remember, right? I'm assuming there's a base level of knowledge here. Because I'm not necessarily on a problem like this going to give you the easiest way of doing it, right? I'm going to have you converting stuff probably. So when you read my question, you got to be very, very careful. Read. Students, you can't blaze through this thing, right? You have to read and understand every question. Physiology is about understanding stuff, and it's applying physics that you learn. It's applying chemistry that you learn. It's applied intro bio stuff that you learn, and you finally getting to apply it in a way that's real to you in a human, because this is human physiology, right? So all of that stuff that you learn actually starts to become important all of a sudden. You're like, I have no idea why I need to learn this in chemistry. Well, now I'm telling you, here's why you got to learn it in chemistry, because now it's going to come back to haunt you, right? So these you can do on your own. It's a cheat sheet. It's a nice explanation. It's tidy. It's one page. I like one-pagers. It's got some examples, stuff all over the internet on it. If you don't understand it, obviously you can ask questions or come to my office. But you're going to have to know how to do this, and you're going to have to do some additional memorization. So with that being said, questions on this. So this is another sheet you have. This is all applied to this osmolarity type question. You see how easy these start to seem all of a sudden when I start talking about penetrating substances. We haven't talked about that. We haven't talked about millimoles or osmoles or milliequivalents. Or we may have to do some conversions. All of a sudden, this problem becomes a monster. Unless you take each part individually and you don't panic. Another philosophy of the Martino class: do not panic. Bad idea. Okay, you got to take it step by step. Learn the steps. Practice the steps. You'll be fine. This is not rocket science. Every one of you can do this. Okay? I know you can. It's going to take practice. So as long as you do that, you'll be fine. Okay, questions? Okay, so the handouts that I gave you, are practice one. So I gave you more practice problems with answers and solutions. So you're going from milligrams to milliequivalents, right? You're going from percent. So whenever you see like 0.225% sodium chloride, that's percent per deciliter. So that's 0.225 grams per 100 mils. Centiliters. So per 100 mils, that's just a chemistry thing. All right? So you have to know that when you see a percentage with a solution, that it's always over 100 mils. Okay. So there's lots and lots of questions you can practice. There's answers, that's number one. And then you have number two, sort of the same idea. They're only a little bit bigger, more complex. People have problems with word problems. They get scared, right? The first one, it looks like it's just math, chemistry. The second one is scary. I have to read. I got to understand something. It's scary. You can't do that. Run away, right? Run away. No, don't run away. Don't panic. You can do this. Same idea. Use all of those sheets. You have the answers. So try it without the answers and see if you can get it right. If you can't, then you got to say to yourself, well, is it my not understanding? Is it I haven't memorized things? So when you first do them, use the cheat sheets, right? Have the sheets with you. It's okay to cheat at first. But ultimately, you got to say to yourself, can I do it without the cheat sheets? That's the ultimate goal. So you have these, okay? So hopefully that's enough. If you can understand all of that, you should be fine. You don't need more. You can on the internet pull off 100 more calculations if you want to do them. Have at it. Right? Some of this stuff, these types of calculations, pharmacists do. Yeah, pharmacists do, anesthesiologists do this kind of stuff. So if you want to go into healthcare, you're going to see this stuff in medical school, in pharmacy school, in PA school, right? In PT school, they make you do physics calculation. In OT school too, right? So you have to get used to doing these types of things. Right? So this is just an addition. All right, questions? Questions from the last lecture, so that's what I'm going to move on to keep rolling with the lecture. We're good? Okay, let's go then. All right. So this is all being recorded. It's part of Camtasia. Unfortunately, you can hear me, but you can't see much going on, right? So that's unfortunate. All right, so if I remember correctly, no, I don't want the beginning. No. Hold on. Okay, I think this is where we should be. Is this where we ended in this class? The slide before this? Which would have been this, and I told you don't memorize the structure of ATP. Yeah, don't memorize the structure of ATP. It's great if you write it on there. I'm not going to give you any bonus. I'll maybe draw a smiley face for you. Make you feel better. I'll draw a smiley face. Okay. So, in these four receptor systems that are in the plasma membrane, these hydrophilic, polar, large substances that need these receptors in the plasma membrane to work, this is what happens. It's an amplification system, right? You have one first messenger, this is a second messenger, and you've already amplified the system by 100 times. By the time you get down to kinases, 100 times. By the time you get down to enzymes, 10,000 times. By the time you get to the very bottom of this, you've amplified this signal 1,000,000 times. This happens very, very rapidly. So that's the important part. So this is exponential. By activating this receptor, you can very quickly amplify the signal 1,000,000 times. You can't do that with a steroid hormone, right? The one where it passes through, you don't get that same amplification. That's one of the reasons why it takes a long time for testosterone and estrogen and progesterone to have its effect, because it doesn't do this. So that's the important take-home message here. Do you have to memorize all of these? No. You have to memorize the concept of amplification. Should you know what basic steps are? You've got a first messenger, a receptor, a second messenger, some kind of kinase, maybe an enzyme, another enzyme-ish. Yeah, general idea. But you don't have to memorize all of these. Just the concept. So a CAMP, and CAMP stands for cyclic AMP. It's a second messenger. System rapidly amplifies the response capacity of cells. Here, one first messenger led to the information of 1,000,000 product molecules. That's a pretty good bang for your buck, right? 1,000,000 times. I mean, if I play the lottery and I spend $2 and I get $4 back, I'm pretty happy. If I amplify that by 1,000,000 times, I'm more than just happy. $2 million, right? Pretty nice. Okay, so here's an example of a picture of how this may look. It might not be a bad example to sort of keep in your memory. So you have some kind of transporter or a channel, right? And this second messenger is activated. It's doing all kinds of things, right? It can be activating DNA synthesis, enzymes. It can be opening channels. It could be slowing down transporters or speeding them up. Right, so this doesn't show because you'll be going to the endoplasmic reticulum. This doesn't actually show the receptor. This is just showing the types of responses you would get. So again, this is a really good, nice, neat picture that gives you an idea of the types of things this amplification system can do. So if I had asked you that type of question, you'd be like, okay, well, it can upregulate or downregulate transporters. It can open and close channels. It can upregulate or downregulate protein synthesis, enzymes. That's what I'm looking for. All right, this is just another example of first messenger system. This is when he's using, remember we talked about G protein couple receptors. In this case, the embedded enzyme here is phospholipase C. It could be adenine cyclase. There's lots of different ones, right? And phospholipase C will then convert this product, this substance here called PIP2 into IP3 and DAG. So these end up being second messengers, and each one will affect a different part of the cell. Just a slightly different system, so more specific than what we did last time. So the summary of the mechanisms by which the receptor activation influences ion channels. The ion channel is part of the receptor. Remember, in the very first kind, the nicotinic acetylcholine ion channel, the one we're going to look at when we do skeletal muscle, that's part of the receptor. A G protein directly gates the channel. So going back here, right, if there's a channel here, you could have a G protein that does where this alpha particle moves over, and let's say this is a channel instead of an enzyme, and then this alpha particle from the G protein would then activate the channel. That's possible too. That's what we're saying. A G protein gates the channel indirectly via second messenger. So instead of the G protein directly gating a channel, let's say the channel is over here. Alpha activates an enzyme. The enzyme creates 2 second messengers. One of these second messenger activates a channel all the way over here. That's what that means. So there's lots of ways that your body can control how a message is sent. So it's not by magic or by chance that things happen in your body, right? It's all very well coordinated and it's very fine-tuned. You, as a human being, are an elegant machine, right? We're at the top of the evolutionary scale right now. So you're about as elegant as it gets. So in these systems, you are a compensating machine. That's what you do. That's how you survive. You are able to compensate because of these very complicated processes that are super fine-tuned. Okay? Helps us survive. You can read this. Calcium is a second messenger. I don't need to read this to you. Calcium is another type of second messenger. So we've seen CAMP is a second messenger. Calcium is a second messenger. IP3 is a second messenger. DAG is a second messenger. So you should know, those you should memorize, because if they come up in a problem, you got to go, what is that? I don't know what DAG is. Then what you talking about? No, now you know. It's a second messenger. So it's part of this type of system. When we get to the way an action potential comes down a neuron and releases a neurotransmitter for a motor neuron, calcium actually is a second messenger. We'll see that. Okay. And again, another example. So this is calcium being a second messenger. These are generic examples. I mean, you memorize them if you want, but you have to understand them. Okay? Understand them. Okay, now we'll stop here for a second. So this is another one you should memorize. This is different. This is called the eicosanoid pathway. It's in your book. Eicosanoids. Now, the interesting thing about eicosanoids is they're highly affected by fatty acids. So whatever the first messenger is here, there's lots of first messengers, right, that can come in here, including aspirin. And aspirin actually does some really good things to this pathway. So aspirin will cause this to happen. It will cause the production, this process occurs, arachidonic acid. Arachidonic acid is a signaling molecule that is pro-inflammatory. So there are certain omega-6 fatty acids that produce arachidonic acid. You don't want to have too much arachidonic acid in your system because it causes lots and lots of inflammation. In fact, this is rampant in this country. We eat way too many omega-6 fatty acids, and we have chronic inflammation that rears its ugly head as lots of diseases, as lots of allergies, as lots of bad things. Okay? So what aspirin does is this particular leg here, cyclooxygenase, you may have heard of. This leg actually splits. This is a really complicated pathway. This is the sort of simplified version of it. There's what's called COX-1 and COX-2. Right? So there's a version 1 and a version 2. The version 2 leads to most of this. Prostaglandins and thromboxane cause clotting. So when you get to be about my age, in your 40s, especially if you're male, and you start taking a baby aspirin every day, what it does is it ends up blocking part of the cyclooxygenase, the COX-2 inhibitor, and by doing that, it causes you to produce less of these pro-inflammatory substances, which means it decreases inflammation, which means you're less likely to have a stroke or a heart attack. Because a stroke or a heart attack is caused by the vessels being inflamed and closing down, and then you have a stroke or heart attack. It's called ischemia. Aspirin, by blocking this leg of this pathway, actually is one step in reducing that. Because these are pro-inflammatory, right? So your body is supposed to be pro-inflammatory and anti-inflammatory. So, they're estimates. These are pie in the sky estimates. We don't know because we weren't around 10,000 years ago. Okay? So, Paleolithic man, we think. We don't know. This is all speculation. Okay? But let's just, for a moment, let's pretend like it's true. Paleolithic man did not have 7-Eleven, did not have Speedway, did not have a grocery store, did not have all of these nasty chemicals that we have created, right? They ate plants. They killed animals. They did lots of activity. The food that they ate was very, very high in omega-3 fatty acids. So this is basically an estimate. How accurate it is, I don't know. It is estimated today that the ratio between omega-6 fatty acids and omega-3 fatty acids, and omega-6s can be both pro and anti-inflammatory, but they can be pro-inflammatory, and omega-3s, the ones you get from fish, you know, that everybody takes the pills for, are really anti-inflammatory. That some people have a ratio in their body right now of 30 to 20 to 1. That means you're 30 times or 20 times more likely to have inflammation at high levels in your body. It is estimated that the normal ratio should be 2 to 3 for the pro-inflammatory to 1. So that means you're slightly in favor of inflammation. Inflammation is a good thing acutely, right? You get a cut, you get inflamed. That inflammatory process brings all kinds of healing molecules in the immune system there, and the cut heals. But when you don't have a cut, you don't want your body to be constantly inflamed. Because if it is, that's what causes cancer. Those are the types of things that cause heart disease, stroke, cancer. So this pathway is part of that nasty process. Aspirin, by blocking COX-2, which is not here, but just a cyclooxygenase, decreases the amount of some of these pro-inflammatory substances that are made. These substances are actually made by omega-6 fatty acids. They're the backbone. So why are people telling you to take omega-3s? Why are people saying you should eat more fish? Well, there's a couple of studies that have been done. The two longest lived peoples on the face of the earth are the Finns and the Japanese. And then third behind them are Icelanders. You know, there's only one thing that they all have in common. They eat per capita 1, 2, and 3. The Japanese, the Finns, and the Icelandic people more fish than any other communities on the face of the planet. And they live longer than everybody else. Interesting, right? So that's part of this. The omega-3s don't cause these substances to be created at high levels. They block. Omega-3s and omega-6s compete against one another. That's how you have to think about it. So that's how this pathway works. What I'm trying to do is, I'm going outside the bounds here. I could make this a really boring lecture. I'm trying to put it in perspective so you can understand how this actually means something to you. It does mean something to you. So it works. You know, the more fish you eat, the better. Plants have a different form of omega-3, right? It's not as efficient as the fish form, but it's also very good for you. Okay. So, if you've ever seen commercials for different types of allergens, anti-allergens, histamines, right? Antihistamines. So, one of them that's been in the commercials recently talks about blocking leukotrienes. Leukotrienes are substances that are made in an allergic reaction. Okay, like Flonase. Have you ever seen the Flonase commercials? And they talk about, you know, Claritin and these other Benadryl only block 1 or 2 of these allergen-type substances. Flonase blocks 6. One of the 6 is leukotrienes. Thromboxanes. Thromboxane is a clotting factor, right? So this prostaglandins are inflammatory. So this entire pathway is primarily pro-inflammatory. So I would memorize this, have a general idea of the types of things that happen and don't happen. Okay? Ibuprofen also affects cyclooxygenase, but it doesn't affect COX-2 but it does decrease inflammation, but it doesn't thin the blood like aspirin. So it affects a different leg of this. Same thing with a leaf, same thing. You know, it's all part of this big pathway. Questions on that? Again, just another response. You can just read through this. This is just highlighting all this stuff we're really talking about. So you should know the basic receptors. So this is important. Not all responses to hydrophilic signals are immediate. Increase in gene expression can occur, and the resulting proteins can increase the target's response. So if this type of receptor system is affecting the DNA, just like testosterone or estrogen, then that's going to be a slow response too, right? Because anytime you want to make proteins or shut down the making of proteins, it takes time. You've got to ramp stuff up, you've got to ramp stuff down. So that portion of this signaling cascade is slow, just like the hydrophobic version. But everything else is super fast. So the DNA effect, this part, is not amplified 1,000,000 times. But a lot of other things have happened in the process. That's the big picture. These are second messengers. You should memorize these. Some of these we talked about. PI3, PIG. The eicosanoids are all second messengers. So in addition, these are also second messengers. Cyclic GMP, cyclic AMP, calcium. They all do something different. So this is another, check that one off the list. That's it. Okay, so we're on target. Questions from either the osmolarity, milliequivalents, penetrating substances, handouts, this. According to my syllabus, we will start on neuronal signaling and the nervous system next. So we're actually going to start to apply this stuff to an actual system. And we're going to continue to apply it to systems. It's a big lecture. It's 124 slides, so it'll take a little while. Questions, thoughts, concerns? All right, have a fantastic weekend. Yeah. So tutoring, if you talk to the tutoring center, they have two that have accepted. They have Alexis Hahn and Nicole Grant. Okay. So they both accepted. If you go to the tutoring center, you'll work through them. Okay. And I don't know how they get paid or whatever. If you have to, I think once they accept, they'll just give you their name, and I think that then you contact Nicole and Alexis. Okay. They're both really, really good. Alexis took this, they both took it last year. Alexis is going to be a biology teacher, so she knows how to teach. Nicole is just really, really smart. So they're both really smart, but they're both really, really good. I would send anybody to them any day of the week. So
there's a specific email for the tutoring center?
Yeah, so the name, the lady's name, let me just shut this down real quick.
Was it Elizabeth?
Yeah, Emily Jansen.
Okay.
Let me see. Yeah, her name is, I always forget. Yeah, Emily Jansen at the tutoring. So if you, and it's with double S, this is Janssen, so it's E. Jansen 1 at Carthage.
Okay.
Yeah. And so we have two right now, which is good. And they're both really, really good.
Yeah.
So yeah, absolutely talk to them. They can break it down for you and go see them.
Awesome, thank you.
You're very welcome. Yes, ma'am.
I have a doctor's appointment, so I'll be able to be in contact.
Okay. Well, I hope you feel better. All right.